Okay, we're going to play around with a power MOSFET, and so I have the MOSFET right here. This is a IXFC 26N50, and so what we're going to do with this is show you how sensitive this is to really small changes in voltage or charge on the gate. So the way I'm going to hook this up is, according to the specification sheet, the pinout on this is gate, drain, source. So our drain is going to our motor, and our source is going to the negative terminal of the power supply. So this is what we're hooking up here. Our drain is hooked to our motor, which is going to our positive terminal of our 12-volt battery, and the negative terminal of the 12-volt battery is going to our source. And this is just acting like a little switch in between ground and the motor and the positive terminal of the battery. Our gate here is where we're applying a voltage, and the way we're going to apply this voltage is by touching the gate and touching one or the other terminal of the battery. If we touch the positive terminal of the battery, it comes on. Touch the negative terminal of the battery, and it goes off. So let's see how that works. So here I'm going to bend the gate up a little bit so I can get my fingers on it. Touch the positive terminal of the battery, and our motor turns on. Now I'm going to touch the negative terminal of the battery, and it shuts off. So all we're really doing is transferring charge into and out of the gate, and that charge stays there. The gate is insulated. Another name for these is insulated gate field effect transistors. So this term insulated gate means that once we put charge, in this case if I'm touching the positive terminal of the battery, I'm pulling electrons out of the gate, and when I do that I leave a positive charge on the gate, and that positive charge stays there until I put electrons back in by touching the negative terminal of the battery. This is what we call an N-channel MOSFET, so it takes a positive voltage on the gate to turn it on, and a negative or a neutral on the gate will turn it back off again if we pull that, put the charge, restore the charge back to the gate. Okay, so positive, negative, on, off. Now these devices are so sensitive that you can even turn them on and off using other sources of charge. And here I have a device. This is what's called a fun fly stick. It's just a small Van de Graaff generator. It's a kid's toy, but it comes in really handy for explaining electrical concepts. I'm going to get this close to the gate and just press the button, and it's going to charge this into this stick positively. And when I do that, the MOSFET turns on. And if I touch the other terminal of the MOSFET and press the Van de Graaff generator button, I can turn it back off again. And the reason this is working this way is when I get this close to the device and I press the button, this end of the stick becomes positive, but the other end of the stick becomes negative, and I've got my finger touching this little ring around the button, and what's happening is the electrons are being pulled away from the end of the stick, and they're going through this ring into my body. So I'm really being charged with a negative charge, and the end of the stick is being charged with a positive charge. So I can turn this on, and then if I turn around and touch the terminal and press the button, I become negatively charged, and eventually I can turn the device back off again. I restore the electrons back to the gate. So it's pretty interesting that a device can be that sensitive that you don't even have to touch it to make this work. Now let's look at some of the things you need to know about MOSFETs in order to use them. The specification sheets have a lot of data, but there's really just a few things you really need to pay attention to when you're using a MOSFET. So here's the specification sheet for our particular MOSFET, and of course one of the things you're interested in is the power for the device, and the power for this particular device is right down here, the power dissipation, and it's 230 watts is what this device can handle. Typically that means the device would have to be on a heat sink, so it can get rid of the heat to a chunk of metal that's going to put it into the air. Another thing here, this device has a fairly large voltage rating. It's 500 volts and has a current rating of 23 amps, which is pretty high, and a 0.2 ohm drain source resistance. And so what this means is that the lowest the resistance of the device can be is about 0.2 ohms. If we scroll down further, we're looking for another parameter here, and what we're looking for now is what we call the transconductance of the device. This is really kind of the equivalent of the gain of the device. If you want to compare it to a bipolar junction transistor, the device exhibits something like gain, but we call it transconductance instead. Transconductance just means that the device exhibits a certain amount of current per unit volt on the gate. And so if you look here, G is the standard symbol for conductance. And if we look over here, we see the device has a transconductance of 21 Siemens. Now a lot of you may be scratching your heads wondering what a Siemen is. And a Siemen is the new term, or the replacement term, for a unit called a mho, which was a unit of conductance. And a mho was simply an amp per volt. So if we look at the way this goes for electronics, we have a unit called the ohm, which is really volts per amp. Volts divided by amps equals ohms. And we have a unit called the mho, or used to have a unit called the mho, and we still use this term. I use this term a lot. I don't like using the Siemen. It just seems to complicate things, and it takes away from this relationship between ohms and mhos, which, they're a reciprocal relationship. A mho is an amp per volt. So for a MOSFET, this makes sense, because if you put a certain amount of voltage on the gate, you will get a certain number of amps. And really it's not quite that way. It's a 1 volt change on the gate will produce a certain number of amp change on the output, or the drain and source. So the unit is amps per volt, really, just like the unit per ohms is volts per amp. And I just mentioned here that the Siemen was formerly called the mho. Okay, so this particular device will provide 21 amps of current for every 1 volt change on the gate. That's all that means. Seems complicated to have just an S that means that, but that's the way it works. Now this doesn't happen immediately. The device doesn't start conducting immediately. You have to be above what's called the threshold voltage. So here we have a unit called VGS TH in parentheses, which means our threshold voltage. It just means gate voltage, gate source threshold. And that voltage has to be, the minimum it may be on a device is 2 volts, and the maximum it might be on a device is 4 volts. Typically it'll probably be somewhere in between, maybe 3 volts. And what that means is that the device will not start conducting until the voltage on the gate gets above this threshold voltage. The reason there's a minimum and a maximum is because when they produce these devices, they don't all have identical characteristics. Some of them are good and some of them are better. If they're really way off spec here, they just get tossed out, or they get sent to some sort of second-hand reseller who sells them as seconds. But the voltage has to be above this threshold before it starts to register a change in current for a particular voltage change. This 21 amp per volt change. One thing about a spec sheet you need to get familiar with too is most spec sheets are laid out this way, and this particular one shows the device itself, and it shows you the pinout, and the pinout is gate, drain, source. Remember, when you're reading a device, you always look at the side of the device with the writing on it. That's the top of the device. And for some devices, the back of the device will be metal. In this particular case, the back of this device is insulated, so it's plastic. But the front of the device is always the side with writing on it. And you'll see the device pinout shown like this typically. Sometimes they'll flip the device around and say that you're looking at the back of the device. I don't quite understand why they do that, but some specification sheets do that. And so that's something you need to get used to, is how these spec sheets are laid out and what are some of the terms in here that you might need to know. This is the symbol for the device, just like I showed in my drawing for the hookup. You have the gate, the source, and the drain symbol here. Sometimes you'll see these drawn with a circle around the symbol. I'm just save some time. I didn't put the circle around the symbol, but here on the spec sheet they did. There's a diode in the device that conducts if you reverse the polarity to the device, and it's sort of a protection feature. What it really does is prevent the device from getting a back voltage when it's switching inductive loads, and so it allows the device to pass those currents instead of building up destructive voltages that can destroy the device. Okay, the next thing we want to look at is different modes of operation for this device. So I'm going to hook up some extra terminals here so I can monitor the voltage. So I'm hooking these to the terminals on my meter to allow me to free up my hands here. And so all I've really done is I'm monitoring the voltage across the drain and the source. So this is our source here, and this is our drain in the middle, and I'm just monitoring the voltage there. Right now you can see the voltage is about 0.02 volts. It's pretty low. The device really at this point is saturated. I've touched the positive terminal of the battery. I've got a pretty large voltage on the gate. It's well above the threshold, so the device is pretty much saturated. If I grab the motor though and put some load on the motor, you'll notice that goes up. That voltage goes up a little bit because I'm torquing the motor down and causing it to draw more current. But still, at 0.4 volts, 0.45 volts, that's not bad. Now, to turn off the device, and we call that, by the way, saturation. The device is pretty much in saturation right now. Now I'm going to touch the gate with touching the negative terminal of the battery, and the motor stops. And if you notice our voltage right now, it's 12.39, which is our battery voltage. So the device right now is in cutoff. All the voltage is dropped across the device itself, and none of it is dropped across the motor. So this is what we call cutoff. Now I can put the device in the active region, which is in between saturation and cutoff, by quickly tapping the gate. And so right now, if you notice, the motor's turning not quite as fast, and the voltage is about 2.15 volts. And if I touch it again, I didn't touch it fast enough. Now it's gone to a really low voltage of 0.2. That voltage I had a minute ago before this reading meant the device was in the active region. So it was in between saturation and cutoff. It's in saturation again right now since that voltage is really low. I'm going to try to put it into the active region by just quickly touching the gate. And you'll notice that, okay, well now we got 0.73. We're in the active region for this device. So if I touch it really fast again, it's 1.57. Touch it really fast again. I'm draining off, or I'm actually letting electrons go back into the gate. So now it's at 0.2. Touch it again and again, and there we got 3.15. So little by little I'm getting rid of that charge, that positive charge that's on the gate. Now it's turning pretty slowly, and it's 6 volts. Now what's happening when we have it in this active region here is that the transistor is getting a little warm because it has a voltage across it and a current through it. And anytime a device has a voltage across it and a current through it, it has a power. It's dissipating power. And so most of these devices are designed to be used in an on-off mode, either saturated or cutoff. But right now we've got it operating in active region. So it's halfway on, halfway off. And so right now it's about halfway. There's 12.41. That's pretty much cut off because all of our voltage for the most part is dropped across the transistor now and not the motor. When we go through this active region, what we're really doing is we're shifting voltage from the device, from the motor or the load to the device. When the two have the same voltage across them, we're halfway between saturation and cutoff, then both devices are using the same amount of power. The motor is converting that power into motion and heat, but the device is converting all that power directly into heat. So when you operate a transistor of any type,